So today we are going to see about applications of Gauss law. Case 3, electric field due to charged infinite plane sheet. That means you have a plane sheet and you have a cylindrical Gaussian surface, very thin cylindrical Gaussian surface. So this plane sheet is just cutting that Gaussian surface. So this is positive, the sheet, the infinite sheet is charged with positive charge. So the key points we have to remember here is, first point, uniform surface charge density. Now we have three types. Here we are going to deal with surface charge density. We have linear charge density and volume charge density. So here uniform surface charge density sigma. That means this infinite sheet which is cutting the Gaussian surface, the cylindrical Gaussian surface, and it is charged with the plus q, and it is the charge density is uniform throughout this plate. Okay. The second point is the plane is infinitely large, therefore E vector is same and equidistant. That means if we can, with reference to this point, whatever charge at a distance, say a distance A, you have just same charge happens to be here, left, right, all around. Similarly, if the distance increases, for the same distance all over, the charge is going to be same, and moreover the infinite sheet is going to have uniform charge density. Okay. The third point is we have to see in the total electric flux for this Gaussian surface. That is integral, closed integral E vector dot dA, and by Gauss law we know that this flux, total electric flux, is equal to the charge enclosed divided by epsilon naught. So now we have three cases: integral E vector dot dA vector for curved surface. So this is the, if you see this is the curved surface. For if you assume this, so this is the curved surface. Okay, for that, and then you are considering this surface which is this side and another surface this side, and the infinite sheet is cutting this Gaussian surface, and the charge density is same. All these things you know. So now we have considered the curved surface, which is integral E vector dot dA vector plus integral E vector dot dA vector at P. P is this area, and the same area lies here also. It is a you are considering P and P dash point, 2 points. So P, we are considering at P integral E vector dot dA vector, that is this side, and the last one is plus integral P dash E vector dot dA vector, which is the opposite side face. Now if you carefully see the curved surface, the E vector is in this direction. Why? Because plus q charges sheet is like this, so electric field will be in this direction. And if you consider a small area, the unit perpendicular vector, normal vector or dA vector, is perpendicular to electric field. That means the angle between them is 90 degree. So you all know that cos 90 is 0. So because of this, the value is 0. So you have only two cases. One is this area and the other one is this area. So the electric field is coming out and you are considering a small area here. The unit perpendicular vector dA vector also lies in the along with the electric field. Both are in the same direction. Therefore, the angle between them is 0. Cos 0 is 1. Therefore, the value of this will be magnitude of A, magnitude of E into magnitude of A. Similarly, if you consider the other side, this side, the electric flux, electric field is directed towards this side, this direction, because of this vertical uniformly charged uniformly positive charged sheet. So E field is coming out. If you consider a small area dA, it is also, and unit normal for that area is also along the E field. Therefore, the angle between the E field and the dA vector is 0. So, cos 0 is 1. Therefore, here again the resultant flux will be magnitude of E into magnitude of dA. So, the curved surface, it is 0. So, the total electric flux coming out of the Gaussian surface is equal to integral EdA at the point P and integral EdA for the surface P dash. This is surface P dash and that is surface P, and we are considering point P and P dash. So, by Gauss law we know that the flux, total electric flux is equal to charge enclosed within that Gaussian surface divided by epsilon naught. So, now we have these two are all same integral. The value of this integral and this integral is going to be same. So, 2e is constant, you can take it out, integral dA, which is equal to q charge enclosed by epsilon naught. But we know from the surface charge density, if it is going to be very small, del q by del s. If you consider the whole Gaussian surface, it is sigma is equal to charge enclosed by area. That means charge enclosed is equal to sigma into area. That's what we are substituting here. So, charge enclosed is equal to sigma into A divided by epsilon naught. Okay. Now, integral dA is nothing but A. So, 2E into A, sigma A by epsilon naught, A gets cancelled. Therefore, E is equal to 1 by 2 sigma divided by epsilon naught. And if you want to say in the vector form, E vector is equal to 1 by 2 sigma divided by epsilon naught n cap. This is vector form. Now, what is the observation you make with this relation? We don't depend on the distance r. E vector is independent of r, because in the final answer, if you see, this E electric field depends only on sigma. Sigma is uniform surface charge density and epsilon naught is constant. You all know that the value is 8.854 into 10 power minus 12 farads per meter. So, the important observation is this E vector is independent of r. You don't see any r in this relation. What is r? R is the distance between the infinitely charged plate and the point of consideration P. This side also same distance r. Therefore, we arrive at this relation where electric field is 1 by 2 sigma. Sigma is nothing but uniform surface charge density divided by epsilon naught. That means E field will vary only because of sigma. What is sigma now? Uniform surface charge density. See, it does not depend on the distance r. Thank you for your attention. That's all about electric field due to charged infinite plane sheet. Thank you. Nandri.